Well, all right. It is our pleasure to have the talk by Matthias Ludewig on the stringor bundle and spinor bundle of loop space.
Yeah, thanks for the invitation. It's been a lot of fun. So I'll talk about some work that we've done over the last couple of years. Lots of it is joined with Peter Köstler and Konrad Waldorf. So this will be sort of the string group was mentioned earlier, and principal two bundles will also appear at the very end. But first, so I think one has to click the screen or something. Oh, yes. This is not focused or something. So, now it should work. No, it doesn't. All right, now okay, all right. So good. So maybe some background on what this is all about, right? So maybe you know index theory, maybe you don't. So it's the index theory of a compact spin manifold. So on a compact spin manifold, you have this Dirac operator, and that Dirac operator has an index, which is just the dimension of its kernel minus the dimension of this co-kernel, and that's an elliptic differential operator, and that acts on sections of a bundle called the spinor bundle that canonically exists on a spin manifold. And yeah, there are analytical results that say that because the Dirac operator is elliptic, but these things are finite dimensional vector spaces, and so they have so this index is just some integer in Z, and then that's like why don't you just look at the dimension of the kernel and the co-kernel separately? Well, that's because the index is a deformation invariant of the operator. Particularly if you change metrics and stuff, then you won't change the index. And that led people to think, maybe there's that looks sort of topological, so maybe there's some topological formula for that. And indeed there is. That's called the Matthias index theorem. It's like one of the most famous theorems of the century. And it says that you can calculate the index of the Dirac operator in a purely topological way. We take a certain characteristic class, which is called the A hat genus, and there are explicit formulas for how to compute this, and then you compare it with the fundamental class of the manifold, and you get this number. And in particular, you can do this, of course, for any manifold, like any oriented manifold, not necessarily spin. And the A hat genus is a rational class, and so a priori you get only a rational number. And it's only true that on a spin manifold you actually get an integer, right? So that's one of the features here that this is sort of an integrality results. So what will be important for what comes next is the case that the spin manifold has an S1 action. So then, of course, the Dirac operator, like you assume that the action lives to the spin structure, and then the action commutes with the Dirac operator, and that means that the kernel and the co-kernel are actually modules for S1. And so that index is like an element of representation ring of your group, phi in general, or yeah, G is S1 here. And well, in this particular case, it's just sort of Laurent polynomials in one variable. And so there's also a formula which is more complicated. And the feature of this formula is that you can calculate the index, so it's the equivariant index, by sort of an integral or by pairing with the fixed point component of the action. And so here n is the normal bundle of the fixed point component in psi m, and that gets an S1 action because so it's like the infinitesimal action around the fixed point component. And so I don't want to explain how to read this formula and what this formula precisely means. Just know that it's like some complicated formula in the normal bundle, which is complicated but entirely explicit. And so then Witten came along and thought, hey, I want to calculate the index of the Dirac operator on the loop space instead of a compact manifold. I want to look at the loop space of some manifolds. So say M is probably a compact manifold, and loop space means smooth loops in my manifold. So that was this famous paper of Witten on the index of the Dirac operator loop space. And so the first observation is that this is actually an S1 manifold because you can rotate loops, right? You can reparameterize by rotation of S1, and that gives you an action on the loop space. And so Witten's idea was to just formally apply this fixed point formula, what we saw, to the loop space. So completely ignoring that this is not a compact finite dimensional manifold, but just like some gadget. We said, well, let's see what comes out. And so the normal bundle, so this is the formula again, and the normal bundle is just a direct sum of, basically it's, the normal bundle is essentially functions on S1 that's valued in some, like the tangent bundle of the manifold. And functions on S1, you can just Fourier expand and you get lots of like infinitely many, like a sum of infinitely many finite dimensional inequivalent S1 representations. And like formally plugging that in and doing some shenanigans, he got to some formal power series in the variable Q. Where that like Q inverse doesn't appear because like actually the N is a real bundle. Instead of, so yeah, if you do it right, then you can write it in such a way that no negative powers do. Okay, so that's what people call the Witten genus afterwards. Sort of a funny construction. And again, like as before, you can define it on any oriented manifold, and it's some power series with values in Q. And now if you start with a spin manifold, though, then you can do some rewriting, and you see that all of these coefficients of your power series are actually indices of twisted Dirac operators. And so in particular integers, and so you get an inchball power series in Q. And then I think it was shown by Xavier, also not much later, I think still in the 80s, that actually this power series that you get at the Fourier series of a modular form under a certain extra topological condition on the manifold, namely that P1 of M vanishes, at least with coefficients in Q. And then sort of quite a bit later, it was shown that, I think by Andon Hopkins and rest, that actually this leads to another cohomology theory called TMF. So there's like a TMF valued Witten genus, and TMF has these mapped to modular forms, so that makes this commute. So that sort of uses it in this like stronger condition, which is that one half. So if you have a spin manifold, you have this canonical refinement of the first Pontryagin class, which is usually sort of a little bit abusing notation called 1/2 P1. So it has the property that 2 times it is P1. And so that's sort of a canonical characteristic class that you can have on spin manifolds. And the string condition is that this characteristic class vanishes. And under this condition, like you get this even more refined Witten genus. All right. So I guess what this has to do with the string group will come out in the end, but for now it's just a manifold that satisfies this topological condition. So what's the deal about this? So there's this famous conjecture of Stefan Stolz that which says that if a compact string manifold admits a metric of positive Ricci curvature, then the Witten genus is 0. So maybe here a comment, because I just discussed this lift to TMF. So this works. So like this thing is always 0 if a manifold is not, the dimension of your manifold is not a multiple of 4. And so this lift still exists, but it's like takes values in the torsion part of TMF. And so the conjecture is true for like the in dimensions that are multiples of 4, and it's known to be false, like for this very refined Witten genus in other dimensions. But so for dimensions that are multiples of 4, the conjecture says that if we have a string manifold that emits a metric of positive Ricci curvature, then the Witten genus is 0. So I know that you're not differential geometers, so maybe you don't care about this, but like one reason why you maybe should care is that, or that why geometers care is that, so there are all these different curvature invariants, right? There's scalar curvature, there's Ricci curvature, there's positive sectional curvature and stuff. And so the point is that sort of Ricci curvature, positive Ricci curvature is a much weaker condition than positive scalar curvature. And we know a lot about positive scalar curvature. But we know sort of very little about positive Ricci curvature. In particular, we don't know any manifold of dimensions bigger than 5 where, say, simply connected, that has a metric of positive scalar curvature, but we know that it does not have a metric of positive Ricci curvature, which is like, even though like Ricci curvature is on paper a much weaker invariant. So this is sort of very embarrassing, and this would like be a huge big breakthrough in differential geometry if this was shown to be correct. Because then we could actually have actual obstructions given by the Witten genus for positive Ricci curvature. And so I guess the reason why Stefan had this conjecture in the first place is that so maybe there's the loop space Dirac operator, we can define it and somehow, and its index is this Witten genus. And the way you show that manifolds can't have positive scalar curvature is using this Lichner-Ritz formula, which is some formula like for the Dirac operator on normal manifold. And the idea is that, well, when we're on the loop space, there's a similar formula that involves the Ricci curvature somehow. Because, well, the Ricci curvature, I mean, yeah. Well, I don't want to go into like what Ricci curvature is, so I want to leave it at that. But that was sort of the hope, and I put hope in green, so to follow your conventions. And so another conjecture that's related to this, and that's maybe more related to things that people at this conference think about, is that that the Witten genus should be the partition function of a certain field theory. So the field theory should be 2 one-dimensional, so it should be super symmetric, which should be one super direction. Should be fully extended, so down to points. Should be Euclidean, so manifolds have a flat Riemannian metric. And there's something else you say what that means about super directions. So that's sort of where the modularity comes from, right? So because like if you have a modular space of tori in the manifolds, and sort of there are these SL2Z acts on the modular space of tori, and this gives you precisely these modularity properties at least if you build in twists also.
Those are different ends.
Sorry? So
The ends are different, right? There's 2 capital M's on your sheet. Right, there's multiple capital M's, and the one in the upper left and the lower right are different.
yeah, those are the same. Those are both M's, but the manifolds that the field theory is defined on are not M. They're 2-dimensional things. The target means that all manifolds are mapped. Yeah, I should say that. So they all have maps to the target manifold, to the end. That's part of the geometric data that's included in the board design.
So I'm a little confused. Did you say that you want M to have a flat Riemannian metric?
No, the boardings have.
Okay.
So the manifolds that map
Okay.
into them have a flat Riemannian metric.
Okay.
And so like you get a function sort of on the if you integrate over M in some path integral thing, then you get a function on the moduli space of all sorts of such manifolds, and that's invariant under the group of SL2Z, and that's where the modularity should come from. That's the field theory explanation for this modularity.
Okay.
And so like related to this is that like field theories of this type, so 2 one-dimensional extended Euclidean field theories should be cocycles for TMF. So that's like the program that Peter and Stefan have been working towards for a while now. And so this actually has been quite recently also applied for string theory. So it's like this conjecture, like under this conjecture, there have been statements made about, yeah, I think like sort of under this conjecture, other conjectures in string theory have been created by Chachikawa and Yamashita, so which I know nothing about, but so that's sort of yeah, one application this has in string theory. So these are two things why this is interesting. So of course the problem is there is no loop space Dirac. Just doesn't exist. So some things exist. So Taubes sort of end of the 80s already constructed some Dirac operator that lives on the formal loop space. So basically it lives on the normal bundle of the fixed. So I didn't say this earlier. So the fixed points under the S1 actions are of course like the constant loops, which are just M, right? So that's one of the parts of the story. And so this Dirac operator lives on the normal bundle inside M. So that operator has the correct index, but the problem here is like if you want to apply this to these things that I just talked about, that won't work because you can't define this operator on any spin manifold. It does not use the string condition anyway. So so the hope here is that you should use the string structure in some way to extend this Dirac operator from this formal neighborhood of the constant loops to the whole loop space, and then hopefully say something that reaches curvature. Yeah.
So maybe still this one using the Schultz conjecture specifically for string manifolds.
Yes.
And it's just the rational damage.
I think, yeah, I asked Stefan this morning. So I think there are no counterexample for like this stronger conjecture that like, yeah, already the rational, like this could also already work for rational string manifolds, I think. But
Yeah.
the conjecture is for really the string conditions, so really the integral vanishing of 1/2 P1.
But I know that rational damage.
I'm sorry?
I just know that it doesn't, that you said already that the Witten genus does not vanish, and the Witten genus itself doesn't vanish. I'm just trying to keep track.
So maybe so I said in passing that like in dimensions not divisible by 4, that it's false, and S3 is a counterexample. Because like there are lots of string structures on S3, and for many of them the Witten genus does not vanish, but it obviously has positive Ricci curvature. So like it's sort of parallel to the story of the A hat genus and the alpha invariant, which is sort of the refined KO valued index. And like there, it's true that like if this refined index is non-zero, then your manifolds, like also in dimensions not divisible by 4, don't emit positive scalar curvature. But so the analogous version of the Stolz conjecture is false. Okay, thank you for that question. Yeah, so in this talk, so there's no Dirac operator, but there's also no loop space spinor bundle really. So maybe let's start with that. So that's what I'm going to do. Okay, so maybe back up a little and let's talk about spin structures in finite dimensions. So say we have an oriented manifold, and on an oriented manifold you can so all my manifolds have Riemannian metrics. So you always have an orthogonal frame bundle, and if you have an orientation, you can reduce that to oriented frames. And the spin structure is now a lift of the principal bundle of oriented frames to the spin group. So like you have a bundle spin M of spin frames. That's precisely what we saw earlier, right? So you have your manifold, and then you have say SOM is the bundle of oriented frames. And then you want some bundle, which I maybe call spin M, and so the spin group acts on this, and there's the morphism from spin D to SOD, and this spin bundle has a map to SOM, and that should be equivariant along this homomorphism of groups. So that's what a spin structure is, and how do you get the spinor bundle? Well, so there's an irreducible graded representation of the spin group. So actually there are there are two irreducible representations of the spin group, at least same even dimensions. So the Clifford algebra acts on this compatibly. So the Clifford algebra, so let me just say what that is, so we're on the same page. So the Clifford algebra is sort of, so it's some sort of, you start with the Euclidean vector space V, and it's an algebra that is, so you have a linear map from the vector space into the algebra, and it's generated by the elements of V, and the relation is V times W plus W times V is equal to -2 times the scalar product of V and W times, so it's unital algebra, so times the identity element. And it's sort of universal algebra with this property. And so that this acts compatibly with the SOD action. So this algebra has an action of the automorphism group of V, so SOV, and for RD it's SOD. And that the representation, so the action is compatible with the representation means that like sort of automorphisms of the Clifford algebra are implemented on S. So here the C means Clifford multiplication. So if you act by an element of the orthogonal group on V and then Clifford multiply, there exists some spin element G tilde such that when you like conjugate after Clifford multiplication, it gives you the same thing. So that's sort of this implementing relation that these two representations satisfy. And what that means is that you can, so given a spin structure, spin M, you may form like an associated bundle, spinor bundle. And it's not only a vector bundle, but it's actually a bundle of graded left modules for this algebra bundle, for the Clifford algebra bundle. What is S here? Well, S, which S? So so there's a curly S, that's the spinor bundle, and that is the spinor representation, which is this representation that's down there. So it's like the canonical representation that the spin group has. Take as a black box here, right? So and then you can form the Dirac operator, and the point is that it's given in terms of this Clifford multiplication, right? It's basically formula is not important, but there it is. Okay, so how do we do this for the loop space? Well, the loop space is a Frechet manifold, and you can say what the tangent bundle is. It has this funny formula. So tangent bundle on the loop space is just the loop space tangent bundle. There's only a reasonable statement if you say what the projection is, but of course the bundle projection is just a footpoint projection of like any loop in the tangent space has a footprint projection to a loop in M. That's the bundle projection. And so what that means is that the structure group of the tangent bundle is canonically reduced to the loop group of OD, meaning that if I just loop the frame bundle, which is then a principal LOD bundle, then I can sort of, my tangent bundle is canonically isomorphic to this associated bundle. And sort of similar, if my manifold is oriented or spin, then yeah, I can loop the respective SOD or spin D principal bundles and get principal bundles for LSOD and L spin D that reduce the structure group further. And now the definition is that was given by Killenbeck in '87 is that a loop space spin structure for a spin manifold M is a lip of structure groups for this like I have a spin manifold, so it's the loop space has a structure group L spin D, and I want to lift this principal bundle to the basic central extension of L spin. So that's a little bit of theory of loop groups. So the loop group of spin M has up to sign, but there's some canonical sign choice you can make. It has a unique central extension that generates the group of central extensions. And that's called L spin tilde. So central extension means central extension by U1. So it's fits into a short exact sequence with L spin on the right and U1 on the left. So that's what a loop space spin structure is according to Killingback. And then sort of what's a fact is that there exists an infinite dimensional version of the spinor representation. So that's a unitary graded representation of this central extension of L spin. And now what you can do is you can take LRD, so that's just RD valued functions on the circle. That has a canonical inner product, just like L2 inner product, and you can form the infinite dimensional Clifford algebra on that. And this algebra will act on this infinite dimensional spinor representation in a compatible way with the loop group representation, where compatible means the same thing as before in finite dimensions.
Is the central extension acting by circle rotation?
No. Like, where does it act? So on S on this representation?
No. So L spin D is a space of loops
Yes.
in spin D. If I give you a map of a circle in spin D, I can rotate the domain circle.
Yeah, that's not what happens. So this extension is actually is equivariant for diff S1.
Loop
So-
rotation is equivariant for the spin D or it's commutes with spin D multiplication. It's just a different central extension.
It commutes with spin D multiplication. Sorry, what?
If I rotate a loop and I multiply group elements pointwise, I can do that before or after rotating.
Yeah, but that commutes, right? So that's the same thing. So there's an action of S1 on L spin D, and I'm saying the central extension is equivariant for this action. There's like this action lifts to the central extension. Right. So you can form a loop space spinor bundle just completely analogously to the finite dimensional case. And it's just as in the finite dimensional case, it's a bundle of graded irreducible modules for this Clifford algebra bundle on the loop space, which you can also form. It's some bundle of graded star algebras. So graded always means Z mod 2 graded. So nice, okay, we have the spinor bundle on the loop space. So that's the problem, right? So that's all stuff that's been done in the 80s, basically, or was implicitly done in the 80s. Of course, if you want to go to the Dirac operator, that's going to be difficult, right? So that's why I guess there was no progress, like, well, one of the reasons. But there's even a more fundamental problem. Namely, that's something that I think was found out by McLaughlin. So the question is, when do these central extensions exist? So when do these loop space spin structures exist? And the answer is they exist if and only if the transgression of 1/2 P1 vanishes. So here's a little cartoon of what transgression is. So you have this map from LM times S1 to M, which is just evaluation. So you have a loop and a time, you evaluate the loop at the time to get to M. And you can pull back degree K cohomology classes to degree cohomology classes on LM times S1. And then, so if you think about Durand forms, then you can just integrate along the fiber. But you can do this for arbitrary coefficients by just using the slant product with the fundamental class of S1. And so you get so transgression is a map that takes a degree K cohomology class on M, arbitrary coefficients to degree K minus 1 cohomology classes on LM with the same coefficients. And so the criterion is now, so this is where the, like, K is 4, then this is where the P1/2 lives, and loop space spin structure exists if and only if its transgression vanishes, and the problem is that transgression needs not to be injective. And so this is weaker than a string condition, and like so there are manifolds where this transgression vanishes, but 1/2 P1 does not vanish. So this loop space spinor bundle may also exist for non-string manifolds, and for such manifolds, it's probably not true. Like maybe I didn't convince you entirely that it's not, but like there are sort of a lot of reasons why the string condition itself should be such important. And so, yes, what's the question?
Yeah, can you explain that slam product with the fundamental class of S1?
No, but like it's just a product that goes like this. So that's the thing that exists in topology.
Like the cat product? Or
It's the slam product. You can go to code chains and find it.
okay, I'll
Look it up on Wikipedia.
yeah, okay.
Yeah, so it's just a thing that exists. But like as I said, so maybe if you think it's clearer what it is if you think in terms of Taran cohomology, then it's really just integration over the S1 variable. And that you reduce the degree by 1. Yeah, so then Peter and Stefan came along and they wrote this draft, which has been on the archive for not on the archive for 20 years. So it's just on the homepage of Peter's because it didn't make it to the archive. So it has a lot of theorems, but not proofs. That's I guess why it didn't make it to the archive. But it had a lot of very important ideas who were very influential, and a lot of people started, trying to prove these things, and I guess a lot of those things are proven now, and that's basically what I'm going to explain. So I guess this talks about how to prove some things in that draft of Stefan and Peter. So the idea is that only under the string condition, there's a certain geometric structure on this loop space spinor bundle, which is called the fusion product. And the structure should make the spinor bundle behave sort of local on M. So maybe it'll become clear what this means, but so very generally, there's this following diagram here. So the idea is that if you have some geometric structure on the loop space with a fusion product, then there's a map called regression that sort of turns this into a higher geometric structure on the manifold itself. And if you have a higher geometric structure on M, then you can transgress this sort of similar to this Taran thing, yeah. So transgression map that the cohomology that I showed you earlier, to some geometric structure on the loop space, which is like categorically lower and has the additional structure of the fusion product. So the classic example of this, or well, classical, well, so that was basically worked out by Konrad Waldorf in around 2010, is that if you have a bundle gerbe with connection on M, then you can transgress this to get a complex. So the bundle gerbe has band U1. And so you can transgress this to a complex line bundle on the loop space that has a fusion product and yeah, something called a superficial connection, which I won't get into. So the way you do this is so I can give you sort of a line that this line model has as a loop gamma. Namely, if you take a loop that's a map from S1 to M, you can pull back your this is wrong. This should be G. So you pull back your bundle gerbe to the circle, and on the circle any bundle gerbe is trivial. And so you look at isomorphism classes of trivializations of this bundle gerbe. And because you have a metric, so a connection on your bundle gerbe, I mean, that's actually U1 towards. So the connections, so the trivialization should respect the connection. Like I won't tell you how the fusion products where that comes from. So that uses this input of a connection. So here, this, oops, it's good one, sorry, this one. Yeah, sorry, yeah, this is the right way. So now to the degression, so the other way around. There it turns out it sort of was discovered later, I think, but it's sort of more fundamental in the sense that you don't really need connections or anything. So you can take any complex line bundle with a fusion product and degress it to a bundle germ on M. So how does that go? So a bundle germ is this thing where sort of, like generally you have a manifold M, so it's sort of similar to what we saw earlier, so manifold M, and then you have some covering of M, which just means that this map is surjective submersion. You can imagine this as like disjoint union of open subsets of M, but it's also nice to have like more general coverings to allow these. And then you look at this Czech cover of this, so like the Czech nerve of this cover, like this. And then in general, you put a line bundle here, and then you have three ways of pulling back the line bundle to Y3, and you want to relate them with something called the bundle germ multiplication. So now let's see if we have a line bundle on the loop space. How do we do this? Well, we take this cover, so we fix some point in the manifold. That's a little bit of an annoyance. You need to do that, and then of course for any point you get equivalent results. But anyway, let's do that. So that's the space of smooth paths in M that start at the point X and like end F anywhere, and then you can just take the anywhere point and map to that one. So that's this vertical map there. So that's like this example, for example, is one reason why you want to allow more general Ys, in particular also like diffeological spaces or infinite dimensional manifolds. It's just convenient. And then, so if you take the twofold fiber product, well, that's going to be sort of the same thing as a loop, right? So it's going to be two paths that end at the same point in M. And so at least it has a map. I'll call that map Yoda to the loop space. So that's this map from this twofold fiber product to the loop space. You pull back your line bundle along. And now if you think about what do you need to complete this to a bundle germ, is precisely the data of fusion product. So the notation that I put here is like the subscripts indicate along which of these maps I pulled back the line bundle. Okay, that's the drop the Yoda. So it's going to be a map from this pullback times this pullback to there's a mistake. So this should be 1, 3, of course, right? So so that's precisely the structure that we need. And and then there's no data here, but there's an associativity condition here. Like the fusion product, if you pull, there are like 4 ways to pull back the fusion product to this 4-fold intersection, and you need it to be associative. Like there's an associativity diagram that the product has to satisfy. Is that showing up?
Yeah.
Yeah, that's a good question that I don't know. Well, I mean, okay, so I guess they should be classified as the third cohomology of M. Oh yeah, actually, so yeah. No, I can answer this. So there's some work by Melrose and Chris Kotka who sort of come up with something with they call fusion cohomology, I think, which is some cohomology on the loop space that sort of takes into account of fusion products, and then so that's sort of one way to give an answer. But then, of course, the result is that it's isomorphic to some cohomology group of M. so really, I mean, this digression should sort of like if you set things up correctly. No, probably it's not. Yeah, it's probably not going to be an isomorphism. So I'm not sure.
I thought you mentioned sort of smooth delete cohomology.
Yeah. Yeah. Okay. So as I said, also for transgression, you need connections. So maybe this is something that I need to pass for now. Yeah.
I'm sorry, I'm a bit slow. Is iota? So I have 2 paths that end at X or start at X.
Yes.
And return between them. What's the picture?
This is X. One path, another path.
Why do they end? Sorry, they start.
Oh, sorry, this is the fiber product. So this is the notation that I didn't explain, and I think that also wasn't explained in the last talk because it's so usual to like people working with that stuff. So this is always the fiber product of two copies of the path space over this map. So yes, it's gonna be so px2 is gonna sit in, yeah, this is the endpoint evaluation. Yeah. And it's gonna sit in and it's gonna sit in this square. So that's what the 2 means, and then you iterate this for any k. So the pxmk is k paths that all have the same start and end point.
There's a slight wrinkle with the tangent vectors, right? So it's not, you don't have a smooth loop anymore.
Thanks for that question. So we actually use our paths that have sitting, no, not sitting instance, those would be sort of ugly,
Okay,
but like
okay.
all their derivatives vanish at the inputs. You could also do sitting instance, but then you only have different logical spaces, and this is nicer. Like this. Okay, any more questions? All right. So now this is an example. So how should this work for the loop space spinor bundle? And the answer is a 2-vector bundle. Okay, so now, what's a 2-vector bundle? Glad you asked. So this is a bundle germ, right? So we have a line bundle germ product, which is associative. And now imagine that, well, I can just put a trivial algebra bundle here and say, well, a complex line is actually a CC bimodule bundle. And I call this not bundle germ product, but bimodule isomorphism. And this is precisely how you generalize this. So you, instead of putting the trivial C bundle, you put an arbitrary algebra bundle here. And then there are 2 ways of pulling back this bundle. And so you put an A2, A1 bimodule bundle, I think you call that M here instead of the line bundle. And now, yeah, there's a map mu that has precisely the same formula. So here you take the tensor product over A2, so the algebra in the middle, going to M13, and then there's an associativity condition over Y4. So that's what a 2-vector bundle would be. Okay, so again, the A2, A1 means like the pullback along this map, respect to this now. Yep.
Is there like a nice packaging of all of this data?
Is there what?
Is there like a nice packaging of all of this data? If I just wanted to think about this sequence of phi, is this like the nerve of a report?
Well, it's you can talk about like these things on simplicial manifolds, I guess. So this is a particular, like this Chekhov is a particular example of simplicial manifold. His father's simplicial manifolds.
Doesn't it look like a functor to the Morita category? If you
I guess so, yeah. Does it look like a functor to the Morita category? And I guess if you say properly, so I mean, so there's like one thing that you have to decide on is like what are bundles? Because that's infinitesimal information. And if you set it up wrong, you made up with flat bundles, which is not what you want. But otherwise, I think it's
Not something I said.
so yeah, so here I guess okay, so one easy way to say this is just finite dimensional algebras. And then and then there's some things you can say about the bimodules, but like maybe that's something that we can discuss later. So one thing to notice is that both bundle gerbs and algebra bundles are actually examples of 2-vector bundles, right? So bundle, like this is a generalization of bundle gerbs, as I explained earlier, but what you can also do is you can just take the trivial cover, y equals m, and then any bundle, any vector, any algebra bundle on M is an example, because you can just take the trivial bimodule bundles of A as an AA bimodule over itself, and that has canonical multiplication out, and so it's an example of this, right? So it's a simultaneous generalization of algebra bundles and bundles. Okay, so now let's talk about what the stringor bundle is. So that would be the degression of the spinor bundle with a fusion product. So this is the operation of fusing paths with the same endpoint. So one thing that happens, you have to turn the orientation of one around. And so what this means is that actually, if you form the Clifford algebra on this loop, and you can form the Clifford algebra for each of these path spaces, then because you turn the orientation around one, you get an inclusion of like one half Clifford algebra and the opposite of the other half Clifford algebra and the Clifford algebra of the whole circle. And this has the effect that, so this was a bundle of Clifford TLM bimodule and modules, so that bundle of left modules, and now if you pull it back here, then it's actually a bimodule. Then it's a bimodule for the Clifford algebra over the first half on one side and the Clifford algebra of the other half on the other side. Yeah.
I just repeat my question, because this is very much not a finite function.
I said this is the easiest way you can go, right? So this will be clear in like 2 slides when I take. So this is an infinite dimensional function. Yeah, that's true, but let's work formally for now to see how we get a 2-vector bundle. So I put this Clifford algebra bundle here on the path space, or there's x's missing everywhere, so I fix my base bundle as well. And then I put here my spinor bundle, which is now a bimodule bundle. And here you see I precisely need the data of the fusion product, right? So I want to have a bimodule isomorphism of like the spinor bundle tensored over this middle Clifford algebra to this other pullback, and it should be associative over here. And the problem is that these bimodules are not isomorphic. And turn them on their heads, they're just aren't. It's like to do with representation theory of Clifford algebras, it just doesn't work out that way. And I think there was also already sort of the idea of Peter and Stefan that you should just complete these to a von Neumann algebra. So basically what they said, which was their theorem, is that after passing 2 von Neumann completions, you can that a fusion product then exists if and only if the manifold is string, basically. And yeah, so what we did is that we developed this theory of von Neumann algebra bundles and Hilbert bimodule bundles. So now Theo doesn't pay attention. I'm answering you the question. Oh, I see. Yeah, exactly. So the way, like, what we need to use here now, like in our application, this needs to be von Neumann algebra bundles and bimodule bundles for von Neumann algebra bundles. And so, well, the upshot is that everything works out as you want them to be. They form a pre-stack of bicategories, and you can stackify them to get a stack of 2 Hilbert bundles. So, and this precisely is the stackification, right? So objects of the stackification, or one presentation of the stackification, have precisely this shape. And so the idea behind all this is that a 2 Hilbert space is a von Neumann algebra. Because sort of, yeah, you can view von Neumann algebras as categorifications of Hilbert space in some way. Why is that true? So one reason is that if you take the endomorphisms of the model unit, it's going to be CC Hilbert bimodules, and that's just Hilbert spaces. Another way to think about categorification is to say, well, I just add sort of algebra multiplications to my thing. So I start with the Hilbert space and add an algebra multiplication. Well, that's not really a von Neumann algebra, but that's sort of close to something called the Hilbert algebra. That's sort of, any Hilbert algebra has an associated von Neumann algebra. And that's sort of a theory that is not really used anymore, but that's what people used sort of a while ago a lot. So that's sort of the idea behind this notion. Sorry, was there a question?
Isn't it conceptually clearer to say a 2 Hilbert space is a representation category of a von Neumann algebra?
Yeah, of course. I mean, representations of von Neumann algebras are Hilbert space. So this is something that that is particular to von Neumann algebra, that actually bimodules are Hilbert spaces. Like if you worked with C-star algebras, they would be the C-star correspondences, which have these algebra valued inner products. And so they sort of look like Hilbert spaces if you squint, but they aren't Hilbert spaces. And these ones are really Hilbert spaces. So now one problem that is specific to this current situation is that if you take like a path, so gamma 1, not a loop, but a path to two different endpoints, and I complete it to a loop choosing some gamma 2, well then I get my spinor bundle and my Clifford algebra for the path acts on the Hilbert space, but the Hilbert space is different for any choice of I should say I fix gamma 2 and choose any gamma 1 to complete this to a loop, and so this will act on the Hilbert space, but the Hilbert space depends on this choice of gamma 1, and so like if I want a von Neumann complete, so basically take the double commutator of this algebra in the operators on the Hilbert space, this sort of a priori depends on which path I choose. And so the theorem that you can prove is that all these completions are canonically isomorphic. So in other words, what theorem maybe how the theorem should be formulated is that all these representations induce the same ultra-weak topology on this Clifford algebra, and so there's a unique like abstract completion that is standard for them. And then also you can prove that they're locally trivial in a nice sense, and you get actually an algebra over this path space. And then, like whenever you fix three paths with the same endpoints, then you take the tensor product, then this is actually an isomorphism where, of course, you have to take the appropriate tensor product for von Neumann algebra bimodules, which is the so-called confusion product. And if you do that, then everything works out at least pointwise. And so this is a stringor bundle, so you take really the fiberwise completion, but you still need this associative bimodule isomorphism. And so by the theorem, this exists pointwise, but when does it exist globally, right? That was the original question. The conjecture was it exists globally only if and only if the manifold is string. Okay, so what's the results? So basically, Crystal and Baldorf, they construct the diffusion product on a spinor bundle that you get from when you loop space. Spin structure is something called fusive. Basically, it also has something similar to a fusion product. And fusive loop space spin structures were known to be equivalent to string structures from the work of Baldorf. So that's sort of a construction that goes in one direction, and sort of one of the things that was open before like I started looking at this more closely was the other direction. And this is actually sort of so this is again the conjecture, right? And so what I wanted to explain to you now is like something called fusion 2-gerb, because I think it's sort of nice. So what is a 2-gerb? So quite generally, you again start with like a simplicial diagram. And one very simple way to present a 2-gerb is just to say, okay, instead of giving you a line bundle over here, I give you a line bundle over here. And then I have like a trivialization of the 4 different like tensor product of the appropriate 4 pullbacks that I get here, which is satisfy some condition over the 5 bundle intersection. And there's a very clear line bundle that you can write down. So given the data of a loop space spinor bundle, you can write down what I call the fusion line bundle, which is just a bundle of homomorphisms from the tensor product to here. And
Different linear ones, right?
yeah, so hom means here bimodule isomorphisms, or homomorphisms. Actually, they're automatically isomorphisms unless they're 0. And because like all these are irreducible representations, there's gonna be U1 many of them, or like C many of them. If I just do hom, it's 9. Yeah, so they're going to be unitary up to a scalar. And then sort of, I mean, yeah, it's a homework to think what the mu is. It's canonically given and satisfies this cocycle condition. So this gives a bundle 2 gerb, which are called fusion 2 gerb for the spinor bundle. And one lemma that you can prove is that, so of course, like that's sort of clear, is that a fusion product gives a trivialization of this fusion 2 germ because it gives you a section of this line bundle. Right? It tells you that this line bundle is trivial. And conversely, the answer is slightly more trivial, more non-trivial, because like trivializations of bundle 2 gerbs are a little bit complicated. And there the answer is that if the fusion 2 gerb is trivial, then there exists some line bundle on the loop space such that if you sort of modify your spinor bundle by this line bundle, then on this modified bundle, you get a fusion product. And so now we have this fusion gerb. What do we do with it? And the theorem is that that is sort of the theorem that I proved last year is that so bundle 2 gerbs have a characteristic 4 class that they're classified by, and this class is precisely 1/2 P1. Yeah, I won't say anything about the proof. But maybe let me make a remark here, which is that even in the case that, so you can just generally ask, when does a loop space spinor bundle exist? Even if your manifold is maybe not spin, you only need that the transgression of the second Stiefel-Whitney class vanishes. Then you will get something that, so this line bundle will then have a grading because all these are graded bundles. And if your manifold is not spin, then this may be either the even, like these intertwiners may also be odd. They may be graded reversing. And so this is an even or an odd line. And so this is what I would call a super bundle 2 germ. And so they have 2 characteristic classes, one in H2 with Z2 coefficients, and that one is precisely, for this one, is precisely the second Stiefel-Whitney class. So it like sort of generalizes to some graded, more general setup. Okay, so the corollary is that a fusion product exists if and only if M admits a spin structure, so that proves what is to be shown. Okay, so how does the fusion product influence or help with the construction of the loop space Dirac operator? Well, the short answer is I don't know, but like I want to take like 2 or 3 minutes to explain what we think the next steps might be. So with Crystal and Bala, so we recently constructed representation of the string 2 group on a certain von Neumann algebra. If you know anything about von Neumann algebras, this is the so-called hyperfinite type 3-1 vector. If you don't, you can just ignore this. It's this basically it's this completion of the path space Clifford algebra in a suitable way. So all this, in contrast to Lovestock, everything in this construction is strict. So we use a strict model for the string E2 group, which consequently consists of like infinite dimensional groups, but that's how it is. And this thing here is the automorphism 2 group of A. And sort of maybe the easiest way to think about this is well, no, I'll just tell you what it is. So it's also a strict 2 group, and the group of objects is just automorphisms of A, algebra automorphisms, or star automorphisms. And like a morphism between 2 star automorphisms is given by unitaries. Namely, any unitary gives you an inner automorphism of the algebra by conjugation, and you want sort of like have 2 possibly non-inner automorphisms phi1 and phi2. I want like phi2 to be phi1 composed with like some inner thing. Then this unitary is a morphism from phi 1 to phi 2. That's how this automorphism 2 group works. So this is sort of a unitary representation of the string group on a 2 Hilbert space. So this is not a smooth 2 group. But again, you shouldn't expect it to be smooth because like representations of Lie groups on Hilbert spaces are also basically never smooth. So this is a perfect analogy to what happens for ordinary groups. And so now, whenever you have a strict representation of a strict, say, topological 2 group G on a 2 Hilbert space, so I'm an algebra, then there exists some associated 2 Hilbert bundle construction, which is, yeah, it's a morphism of stacks of principal G2 bundles to 2 Hilbert bundles. So there's like a construction that we came up with. It's a little tricky, but not, yeah, super hard, I would say. It's a canonical thing that exists. And so in particular, what you can do is, so a string structure on a manifold, so this is now the point where I say something about string structures, is a lift of structure groups from the string group to the string D2 group. Yes, that's basically what happened in Laura's talk earlier, except that things are not discrete, but I guess smooth. And so yeah, so this theorem that Conrad proved basically is that this is equivalent to that. So the datum of such a string structure is equivalent to that of diffusive loop space spin structure for it. And so now there's this diagram that you can write down. So you can start with a string structure. You can turn it into a diffusive loop spin structure, and then you can construct this loop space spinor bundle with fusion product, and then you can degress it to Hilbert bundle, or you can just form the associated bundle directly. And so the theorem is that this diagram sort of commutes. So I don't think that, like in the literature, any of these things are really set up as proper categories. So so what we do is like for each string structure, there are like concrete 2 vector bundles that you can write down, and what we provide is for each string structure in a canonical way an isomorphism between these two vector bundle, which is actually a strict isomorphism of 2 vector bundles. So that's the state. And so why might this help? Well, I think so this allows you to sort of work with the like on the level of principal bundles, right? And they're maybe much simpler to understand things like connection data and stuff like that than in this sort of, yeah, in this von Neumann algebra setting. Maybe I should also say that these von Neumann algebra bundles are of course not smooth because like their structure groups don't have smooth structures. So it's probably something I should do is you work on this principal bundle level where everything is smooth, and then afterwards, once you figure out what the data is, you associate, see what happens. So yeah, that's thanks.
This is another vector bundle.
Mm-hmm. Yeah, so actually when your manifold is odd dimensional, then you need to take this vector bundle because otherwise you can't find. So this has to do with yeah, for the construction of the spinor bundle, you actually need a Lagrangian in your space. This only exists if you have these, like in the odd dimensional case, only with aperiodic boundary conditions. So this also plays a role, and like, yeah, it's also there. I mean, again, all these things should sort of be part of field theory, which is probably defined on like these 2-1 Euclidean field theories. Like in particular, the underlying manifold always comes with a spin structure, and in particular, the one-dimensional manifolds have spin structures. So everything should be defined for paths with spin structure. So yeah.
Yeah, maybe I have a somewhat naive question. So you, in the beginning, you were addressing or asking how to construct those Dirac operators on loop spaces. And right, there are those sort of homogeneous examples. If your manifold is a Lie group, right, then kind of people were looking into some infinite dimensional Lie algebra constructions, and maybe in relation to this Fried-Hopkins-Telemann calculation of twisted K theory of compact groups. How that, right? This are those 6 examples of what you want to do, or how is it all related?
No, I don't think that this is. I don't see a direct relation.
Because there are also whatever various calculations with bundle jobs and with infinite dimensional spinor bundle of the loop group. At least, let's say, superficially the words
Sure.
sound the same. So of course you look at it in more generality for any M, but compact group typically has a metric of positive curvature.
Yeah. So I'm not entirely sure, but I think it's no coincidence that sort of the same things appear, because like whenever you talk about loop spaces and stuff, it's just what comes up. But I think it's not directly related. So I don't see, or at least I don't see how this would give an example.
So Gregory Landweber did produce that even for homogeneous spaces, and he has, as you said, sort of a representation theoretic approach to saying what you mean by a spinor on the loop space. And he has written down a perfectly good version of this Dirac operator, and it satisfies this wonderful property that, yes, as you pointed out, you have positive Ricci curvature on such a homogeneous quotient target. And in fact, his Dirac operator is invertible. So that was good news from our point of view. The direct relationship is not clear, since we don't know how the Dirac operator on a general target works. But at the end of the day, no, it should be exactly what they are looking at.
Okay, good.
Yeah, that's what I had in mind, that maybe once your general theory is constructed, it had to become like examples of that theory. But
Okay, good. Yeah.
So I have a very naive question. Okay. So these bimodule isomorphisms, if I look at the graphs of them, so that's some half-dimensional subspace, roughly speaking, inside of the domain times the codomain. And it looks like it gives a polarization of this Hilbert space called domain direct sum codomain. And Presley-Siegel's book on loop groups talks about a de-looping of Bob periodicity that essentially says that, if I want to de-loop KU, for example, and understand this in terms of differential operators, the de-loop space looks very much like the moduli space of polarizations on a Hilbert space. So the fact they're using the Morita 2 category for algebras makes me wonder, is there some connection between the fact they're using the Morita 2 category and the fact that you're seeing at the 2 level things that look like polarizations between this de-looping of K theory?
That was a naive question.
Polarization looking.
So of course, like polarizations show up here because like I didn't tell you what the S was, and that is just it is like one way to construct the spinor representation is you take a polarization of your space. It should be an appropriate one for what's like in order to have the loop group act on it. You can't take any one. Basically, I think it's sort of more or less unique. You can take, and then you can take the exterior algebra on it. Different algebra acts on exterior algebras. And so that is very important that we do these things, and like also for like in order to get the right algebras here, it is sort of very important to take the right polarizations. But I'm not really sure if I'm answering your question.
So from your perspective, it shows up one category level lower. Like it's not showing.
Oh, yeah. I mean, so what's there sort of in the background is that there's functor, which I call second quantization from like Hilbert spaces with a real structure and Lagrangians as morphisms, which in this context mean that the complex conjugate is orthogonal to the space itself. And the functor should be like some exponential functor to algebras, and should vector spaces to Clifford algebras and Lagrangians to bimodules on these Lagrangians. And then there's this thing that this functor is normaliz, and that's precisely what makes it interesting sense. So that's sort of how I think about these things.
Is there an approach to the index loop space in terms of, say, like a random torus, this kind of stochastic approach?
No.
So I've certainly thought about it, but I don't. So you're talking about like Brownian sheets or something like that. Yeah. So I know very little about this, unfortunately, and I think that should be something that people should think about. But there's like very little overlap of the community who do stochastic analysis. They usually do that in Rn and things like that, and the community who cares about things like that. So I think there's certainly possible that something could be done there.
Stochastic analysts have an Ornstein-Uhlenbeck operator on path spaces, which is sort of like a Laplace type operator on a path space. And so I thought, oh, that's great. You just need to go from the path space to the loop space, and from this Laplace operator to the Dirac operator, right? Which would be harder, right? But then I came across things, oh, if you do the things on like this Ornstein-Uhlenbeck operator on the loop space, sometimes you don't have a spectral gap. So at that point, I gave up and go like, okay, no, then what you do? So I've given up on this sort of stochastic analysis approach, but maybe that was prematurely. It would be very desirable to have what you're saying.
Let's think, Matthias. Okay. And we will have a lunch around the globe. Maybe national visits. Yes, national visits. That's just kind of amount.
So where's the kind of
Around the globe. So, not the actual globe, but